Okay, so in this video I'm going to have a look at this particular proof here, or this particular statement. We're going to have a look at proving it. So we're going to take p as being a prime number and a as an integer. And if p divides into, this line here just means divide into evenly, divides into a squared, then p will also divide into a. So for example, if you take let's take the number 3 and we'll say that divides into 36, which we know it does. Well, we know that 3 here will divide into 36, which is just 6 squared. 6 is our integer, 3 is our p, 6 is our a, so we've got our a squared. 3 will divide into 6 squared. What we want to show is that 3 will also divide into 6. Well, we know 3 divides into 6. So that's it really, numerically speaking anyway. That's just one example. So let's have a look at it algebraically. We need to prove this algebraically, not just by taking individual numbers and trying it out. So let's take our prime number as being p and our integer as being a. Now just to remind you as well, by the way, prime number is 2, 3, 5, 7, 11, 13 and so on. These are all prime numbers. Now they're prime numbers because they only have two factors. The two factors are 1 and the number themselves. So for example, if you take 11, the only two numbers that will divide into 11 are 1 and 11. No other number will divide into 11. So that's your prime number. So we're going to take our prime number here as p, our integer as being a. So let's have a look at this integer first. Now we know that any integer can be either is a prime number itself, or it can be written as the product of prime numbers. So a here can be written as the product of prime numbers. So those prime numbers will be, let's call them f1, f2, f3, f4, all the way up to let's say n. So our integer can be written as the product of prime factors. These are numbers, prime numbers. Each of these f's is a prime number and it's a factor of a. So when we multiply all of these prime factors together, we'll get a. Now if we take a squared then, which is what we were interested in, we just square the right hand side, so we square each of these, so we get f1 times f1, f2 times f2, f3 times f3, and so on, f4 times f4, all the way up to fn times fn. So this is our a written as the product of prime factors. This is our a squared here written as the product of prime factors as well. Now let's take the p then that we've got here. So we have p, which is our prime number. Now remember, these are all prime numbers here, and this p here is a prime number. And we start assuming that p will divide into a squared. So p will divide into all of this here evenly. So if p is a prime number and all of these are prime numbers, and p divides into the right hand side, p must be one of these prime numbers here if it divides into it evenly. So p must be one of these f's along here. So let's take, for example, that p is, I don't know, let's say f2 here, okay? So p is our f2. Now if p is f2, in fact all of these f's here are also contained in our product of prime factors for our a. So we can say then that if p divides into a squared, p must be one of these f's. In this case we've chosen f2. So f2 must also be one of these prime factors up here. f2 is also contained up here as well. So p will also divide into a. So if p divides a squared, then p will also divide a. And that's really it in terms of this proof here. Now, as I said, the reason we did this was because in a subsequent video that I've done where I proved that the square root of 3 is irrational. So I proved that the square root of 3 is irrational. And I just simply make this statement halfway down through that proof. that if p divides a squared, then p divides a. And I don't actually go into any detail as to why that's the case. So this really just maps that up, if you like. And remember that the 3, we're trying to prove that the square root of 3 is irrational. Now 3 is a prime number. 3 is a prime number. So the square root of 3 is an irrational number. Now the square root of any prime number is in fact irrational. So the square root of 5 is also irrational. And so on. The square root of 7 is irrational, and so on. So you can use it for, to prove that, as part of the proof, that any of these square root of prime numbers is an irrational number.